discussion. So in the previous discussion I have introduced the thermally developing problem. Okay, so here I will formulate the problem. So if you have done the previous discussion, I hope you are clear about the problem description, right? Okay, so now let us do the problem formulation. So firstly we have to determine that um, the order of magnitude of entrance length, that is xc, okay, entrance length, or let me call it ZE because this is our Z direction, okay, because this is Z direction, right? Okay, ZE. So what, how can I find the order of magnitude of this ZE? See here, where the flow is thermally developing, it is analogous to the case of a flat plate flow where I was having, so this was my delta T, and here also this is my delta T. So if I consider half of the pipe domain, okay, so then I can see that this is alike the flat plate thing, right, flat plate thing. So therefore the analysis, if I do the analysis of the flat plate, the order of magnitude analysis that I have already done, only difference will be here we will have a predefined order of magnitude of u, okay. So in the flat plate what I was having was, for Prandtl number greater than 1, I was having different u, that is u was of the order of, from the scaling analysis, delta T by delta, right, into u infinity. So this was for the Prandtl number greater than 1, and for Prandtl number less than 1 I was having this one, right, because for Prandtl number less than 1 I was having delta H by delta T less than 1. So almost all of the part of the delta T is coming beyond delta H. So we have considered a slug flow approximation, okay. Okay, so now this was valid for the flat plate, for flat plate. Now what I will do here, for the pipe flow I am having a velocity distribution of W is equal to 2 into W average, okay, 2 into W average into 1 minus small r by capital R whole square. So here W max is equal to 2 into W average. So here this W max is predefined by the problem, okay, because this 2 into W average is set when you define the problem, and it will be the, and it will be, and this W average is equal to the, this velocity, this inlet velocity, because average velocity cannot change, okay, average velocity cannot change for an incompressible flow with a constant cross sectional area, average velocity cannot change, okay, because the mass flow rate has to be conserved. So because the average velocity cannot change, that means the W max is also fixed whenever you define this problem, right. So unlike this flat plate thing, here the order of magnitude of W will always be W max, right. So it is alike this thing, that is, for Prandtl number less than 1 my u was having an order of magnitude of u infinity, and here also my W is having the order of magnitude of the W max, and which is predefined by the inlet velocity, okay. So here the same analysis will be valid that we got from this one, that is considering u is of the order of u infinity. The same analysis will be valid here. Okay, and from this analysis we got delta t by x is of the order of RE into PR whole to the power minus half. Okay, obviously this is REX, and here for the pi flow we are considering this as the z coordinate. So I will write delta t by z is of the order of REZ on the characteristic dimension for RE is z. So this I know. Now you see that at the verge of being thermally fully developed TFD, I will have delta T almost of the order of d by 2. Okay, I hope this you can already uh, visualize that this is the place where the flow is becoming fully developed. So from this onwards it is becoming thermally fully developed, but here also this del T is almost equal to d by 2. Okay, so if I write this here, so at this stage, at the verge of being thermally fully developed, I will be having d by 2z, right, and that will be of the order of REZ whole to the power half into PR whole to the power half, right. Now you see that and this d by 2 I can write as R. So R by Z is this, and if I break down a RE on the basis of Z, that will be U, right, that will be U, or not U, W, because this is the Z component of the velocity, W into Z by nu whole to the power half PR whole to the power half, right. So then I will be having, so here what I can do is, if I want to bring RED here, so this is REZ, so I want to bring RE based on R. Okay, so then what can I do? So I can take REZ here, that is okay. Sorry, this was minus half. Okay, so here I can write nu by omega into R whole to the power half. Okay, so I have brought here one root r, so I have to multiply one root r here, and here I was having a root z, and here I was having Prandtl number whole to the power minus half, right. So now this r and this r, so this will cancel out and there will be a root, this will be cancelled out, there will be a root. So now I will be having root over of r by z. Now this term is what? This term is my RE based on R radius whole to the power minus half, and this is already Prandtl number whole to the power minus half, and this is equal to RE into R into PR into whole to the power minus half, and this is Peclet number whole to the power minus half. So that means my Z by R is of the order of the Peclet number. Okay, and that means the order of magnitude of the Z, and that is nothing but the ZE, the thermal entrance length, is RE into of the order of PE. Okay, so I got the order of magnitude of the thermal entrance length. Okay, now you see that if the Z is the, if the Z by RE, R into PE is of the order of 1, then I can say my delta T is of the order of d by 2. If my Z by RE, R into PE is less than 1, then my delta T is less than d by 2. Okay, so that means the governing parameter within the entrance length is this. So this is the governing parameter governing parameter within entrance length, right? Okay. So now I can define a non-dimensional parameter, that is z star, and that will be equal to z by Re into Pe, and this Pe is based on D or R, PER, okay, because the Re was based on R, right? Okay, and also I define a parameter theta, that is the non-dimensional temperature, will be T minus T wall, T in minus T wall, okay, and then also I define eta, that is equal to small r by capital R. So now I will have my energy equation, that will be what? So for large PE, okay, for large PE let us write the energy equation first. So first obviously steady case, rho Cp into steady case. So therefore, and also the flow is thermally fully developed, okay, so that means the r component of the velocity is 0, only the w component will be there, and the flow is axisymmetric, that is why the theta component is 0. Uh, I have already explained these things when I was solving the uniform heat flux conditions, so I am writing it directly. So this will be rho Cp into W del T del Z, right? This is the convection part, and now I will have the conduction. So first write the simpler part, that is the axial conduction, then the transverse conduction or the radial conduction. That will be 1 by this into eta into del T del eta. Okay. So now if I put this dimensionless parameters into this equation, then I will get what? Then I will get W, and I know the value of this W actually, okay, because it is fully developed. So W is equal to, okay, I will write it later, W is equal to 2 into W average, that I mean Hagen-Poiseuille velocity profile. It will be theta, and this will be Z star. So I will multiply T in minus T infinity, because I have introduced theta here, and then it will be R into PE. Then I have to multiply K, now K by rho Cp. I am bringing this rho Cp into the denominator of the RHS, this will be alpha. Then I will be having this, so this square, okay. Now both here I am having T, so I will take the T in minus TW out of the bracket, and it will be cancelled out with the LHS, and here I will be having 1 by R into Peclet number whole square plus 1 by, okay, so this was R not eta, because I have not non-dimensionalized it yet. So this was R del R, R del T del R. Now I am bringing the eta, so it will be eta del eta, eta del theta del eta, okay, and one obviously 1 by R square will be there, and we will having the T in minus TW. So I will be cancelling out these two. Then my equation becomes, so now let me put the value of W, and that is 2 into W average into 1 minus eta square, okay, and then I am having this thing Z star into 1 by R into PE. then I will be having alpha by r square pe square, this thing, right, plus I will be having 1 by r square del eta, sorry, not this one, I will be having 1 by r square 1 by eta del eta, eta into del eta, okay. So this one, this is my equation. So which things I can cancel out? So I can cancel out this r here, right, 1 r here, here and here, okay. So then you see that all these are non-dimensionalized, and these are non-dimensionalized in such a way that is the order of magnitude of theta. You see that the order of magnitude of theta is here 1, because the maximum value of t is 1, that is t in, right, maximum value of t is t in, okay. And so this is 1, and this z we have already, I have already told you that within the entrance length, this is the order of magnitude of z. I have proved this, and so this will be also the order of 1, right. And here this is obviously the order of 1 eta, so everything here is the order of 1. So then I can have this, you see, so this whole thing, okay. So this whole thing is of the order of what? 2 I can omit, so W average by PE, right. So now you see a very subtle concept, that you can argue this, that this eta is of the order of 1, that means eta square is also of the order of 1, then this whole thing should be of the order of 0, because I have 1 minus eta square, but eta is of the order of 1, but it is less than 1. So if I get eta square, then it is much less than 1, okay. So eta square is not of the order of 1, it is much less than 1. So that is why 1 minus eta square is of the order of 1, okay. So I got the order of magnitude of the LHS. Then I have the order of magnitude of this one, that is alpha by r into p square, and this I will have my 1 by r only, right. Now you see that if I have to compare these things, I have to have some same numbers, right. So here I have W average, I have alpha. How can I compare this? So one number that takes both W average and alpha is the Peclet number. How? Peclet number is Prandtl number into the Reynolds number, and that will be W average, okay, into, I am writing the Reynolds number based on the diameter, so 2r into, I mean by nu, and Prandtl number is nu by alpha, so that will be W average into 2r by alpha, right. So what I can do is I can multiply all the equations by 2r and divide them by alpha. So from this line I multiply all the equations by 2r and divide by alpha. So in the LHS I am getting W average into 2r by alpha into 1 by PE. In the RHS I am getting, so I have multiplied by 2r divided by alpha, and I was having 1 by r Peclet number whole square. Then I was again multiplying by 2r and dividing by alpha, okay. And I have committed again a mistake here, because here the alpha will be there, because alpha was multiplied to this whole thing. So and here, so there will be alpha, Okay, now this alpha is being cancelled out there, and here this r is being cancelled out, and here I was having one more alpha, and this alpha will also be cancelled out. So now let us see that what we are having. So we are having, this is Peclet number, right? This is Peclet number. So Peclet number here and here will be cancelled out. So this will be of the order of 1, and here this thing will be of the order of 1 by p square, actually 2 by p square, but we don't take this 2, okay, and here it is of the order of 2r, right? Okay, so is this r extra? So this is of the order of alpha by r. I am multiplying by 2r uh, and dividing by alpha. So here also I was having an r. So this is of the order of 2. So order of 2, there is nothing called of the order of 2. Okay, so these are, so this is of the order of 1. This is of the order of 1, and this is of the order of 1 by Peclet number whole square. So I can neglect this term compared to this and this when my Peclet number is large, right? And this term, this 1 by Peclet number whole square, this was originating from this axial conduction term. So therefore I can neglect the axial conduction. So I could have told this in the beginning, that because the Peclet number is large enough, we are neglecting the actual conduction, but because this is a bit different problem, that is the thermal entrance problem, I am deriving it from the scratch. So that means my problem becomes 2 into W average, okay, 2 into W average into 1 minus eta square into del theta by del z star, that is equal to what? My 1 by eta del eta into this thing into alpha, right? Okay, so if it is correct or not, let me see. It should be correct. Okay, 1 by r square was there, and here re into re into p was there, right? So then we got the thing. So let me modify this equation. So 1 minus eta square into del theta del z star is equal to, now here I have alpha by r square, so into r into pe I am taking all the things into RHS, all the constants, and 2 into W average in the denominator. So here 1 by eta del eta, eta into del theta del eta. So here this will be cancelled out. Then I am having this as 1. See, because 2 into W average into R by alpha is equal to Peclet number. So one Peclet number in the numerator, one Peclet number in the denominator, those are being cancelled. Fine. So then my final equation is this. Okay. Then my final equation is this. This is the governing equation. Now my boundary conditions, so let me write the boundary conditions. So at eta equal to 0, I have my symmetry condition. Right? At eta equal to r or 1, I have this is equal to 0 because theta is was what, t minus t wall by t in minus t wall. So at eta equal to 1 my t is equal to t wall, and at z star equal to some initial, and that I call at 0 because z star is z by r into pr. So at z equal to 0 z star is also equal to 0. So at z star equal to 0 I have theta equal to, so t was equal to t, so that means here is 1, right. So this 2 comes from this definition of theta, this one and this one. So along with the governing equation, this thing, this the problem given by these equations are called the Graetz problem. Okay, so these are called the Graetz problem, and this number, that is the z by z by r into pe, this is called the Graetz number. Okay, so you can search in the net that either this number or some constant multiplied by this number, so this is called the Graetz number. Okay, so actually I am having the confusion about the definition of the Graetz numbers, so but what has happened, I am sorry, sometimes this Microsoft OneNote misbehaves. I apologize for that. Okay, so okay, so this is the Graetz problem, or you can say, I mean, many of the authors they say that it is a Graetz-Nusselt problem. Okay, so I have the Graetz problem, so then, and I have the boundary condition. Now your task is just go back to the equation for psi in the uh, in the problem of forced convection in a pipe with UHF, uniform heat flux. So there we have divided the actual independent variable T into 3 independent variables, psi, phi and Tb. So for the psi, the governing equation and the boundary conditions were like this, this problem, and I told you that I will solve this Graetz problem by the method of separation of variable, and you have to solve you have to solve for psi for that problem using the same method. Okay, so now let me try to solve that. So you see theta is a function of eta and z star, correct? Okay, so separation of variable, there can be various ways. Okay, so we write here, so this is uh, this is a mathematical method. Okay, so theta is equal to maybe a of eta into b of z star. So there can be other forms also. You can have something like plus something, okay, plus maybe a square of something, okay, you can have that, but here we take this form. Okay, so now you put this thing into the governing equation. So 1 minus eta square. Now you see that this that with respect to z star, eta is a of eta is a constant. So a will be in the outside and this will be db dz star, not del b del z star, and this is equal to 1 by eta. Now it will be dd eta, not del del eta into eta. Now del a del eta, okay, because b is not a function of eta, so it will be out. Okay, so now I can write it in another way, that is 1 by b db dz star is equal to 1 by 1 minus eta square into eta into 1 by a d d eta eta dA d eta. Okay, so 1 by eta. Okay, so I have got that. So this is correct. So you see that this one is only a function of z star, right? And this one is only a function of eta, right? And for all values of eta and z star, this is true, and this is only possible if both are equal to a constant. Okay, so I think this argument is pretty clear to you. That is, I have a function of a sole function of z star is equal to a function of the single variable eta, and this is true for any pair of eta and z star. So this is only true when both are equal to a constant. Okay. Now what should be this value of constant? So let me call it as mu s, and it is termed as separation constant. Okay. Now you see that if I directly solve here, dB by B is equal to then mu s into dz star, right? That means B is equal to e to the power mu s into z star into some constant, maybe c. So now you see that if mu s is positive, if mu s is positive, then as z star tends to infinity, that is the far downstream in the pipe, my b goes to infinity, and if my b goes to infinity, my theta goes to infinity. Can that happen? I mean, without any reason, we are heating the pipe, but the pipe, I mean, inside the pipe, the fluid is carrying the heat down. Okay, so why should the temperature shoot up to infinity? So that is not physically possible. That means this mu s cannot be negative. So this mu s cannot be negative. I mean, sorry, this mu s cannot be positive. So this is the physical way of understanding this. But in the if you consider, if you go through a formal book of mathematics, then by integrating this equation, okay, that is integrating, you can write, you can take this equation actually, and you can integrate from 0 to 1 to show that mu s must be constant. Okay, I mean, sorry, that mu s must be positive. Sorry, mu s must be negative. So here we know that now mu s is negative. So I take mu s is equal to minus lambda square, where lambda is not equal to 0. Okay. Okay. So this is my separation constant. Now that means I will have here b is equal to e to the power minus lambda square z star into some c. So this is the solution for b. Okay, I am not applying the boundary condition now. Why, you will understand that later. So now let me solve for the eta, for the a. So the condition is 1 by eta into 1 by 1 minus eta square into 1 by a d d eta into eta into d theta d a d eta. Okay, that is equal to minus lambda square, correct? Okay. So now I have that, right? Okay. So now if you solve this equation, Okay, this plus lambda square into eta into 1 minus eta square, that is equal to 0. Okay, now this equation has a very complicated solution in terms of mathematics. So the solution is, I mean, this cannot be solved in a very easy way. There are mathematical methods to solve it, but now the our next objective is to find the Nusselt number, the wall heat transfer, okay, all those things. So if I have to tell you all those things in a pure mathematical manner, I cannot proceed with this equation. But this does not mean that uh, whatever we have done till now all goes in vain, because you have learned that how to formulate the Graetz problem and what is the Graetz problem. Now this is the Graetz problem for a pipe, I mean for an isothermal pipe. Okay. Similarly, we can have Graetz problem uh, for uniform wall heat flux case. Okay, and also this was for a pipe. We can also have the same thing for a set of parallel plates. So parallel plates channel can also have the same formulation, and that will be called as the Graetz problem for the parallel plate channels. Okay, now let us take the same thing. Okay, and now you know that, I mean, I don't have to formulate the problem from the scratch, because now you know that what are the assumptions, right? So you know that how to uh, take up the problem up to this step, that is the formulation of the separation of variables. Okay, now let me take up uh, another problem. Okay, and that is the Graetz problem. Okay, so that will be the Graetz problem for parallel plate channels. Okay, and the problem description is something like this. That is, we have this as a plate and this as a bottom plate. Okay, and there is a fluid that is flowing. Okay, so this fluid is flowing and it is having the uniform temperature U. Okay, and this is our coordinate system. Okay, so this is the origin at the entry point. This is X, this is Y, and this is Z. Okay, so previously we were working with the R theta Z. Okay, but this is a parallel plate problem, so it will be convenient to take up a Cartesian coordinate. Okay, now the plates are having the boundary condition as this plate at y equal to 0, this is the lower plate. So at the lower plate I will be having my Q1 is equal to 0, that is, it is insulated. Okay, and the upper plate, it is maintained at a constant temperature T1. Okay, so this is T2 equal to T1. So this is my problem description. Okay, so now the velocity profile is given inside the pipe by the slug flow approximation. So there is something called a slug flow approximation, and this tells that for a very small Prandtl number, okay, we can assume that the velocity boundary layer is growing very slowly. Okay, that is the velocity boundary layer is like this. So this is the velocity boundary layer. This is growing like this. Okay, that means it will take a very long time to be fully developed. So we can assume that the velocity profile is given as u into ex plus 0 into ey plus 0 into ez. Okay, so we only have this u component, that is the x component. So u is only having this component, so u bar is u ex. Okay, so earlier we were having w equal to 2 into w average into 1 minus r by r whole square, but here we are having only a simple constant u, small u. Okay, so now our energy equation will boil down to, okay, so our problem description is to solve the thermal entrance problem. Okay, so now the same thing, that is, if we write the governing equation, that will be u into del t del x. Okay, because v is 0, w is 0, and it is a steady problem. Okay, so that will be equal to what, alpha this thing plus this thing. Okay, now I have shown that if the Prandtl number, sorry, if the Peclet number is high, okay, so if I have also been given, that is the, it is under the problem description, that is the Peclet number is high, then we can show that the axial conduction term that can be neglected. Okay, and how you can show that? So I have already told you that within the thermal entrance region, x is having the order of magnitude of what? I mean L into PE. L is the characteristic length towards x. Sorry. L is not that. It is also under the problem description. So L is nothing but the vertical distance. So previously it was given by r, but here it is L, the vertical distance between the plates. Okay, so x is of the order of this, and in the previous problem we shown that there z was of the order of r into p, right? So similar thing. I am not going to the details that how we got this, right? And then y is of the order of L. Okay, let us say that t is of the order of some tc. Okay, so then if you write the order of magnitude of this term, then what will be this? That will be u. U is having only a value u, so this is the order of magnitude is u. U into tc by L into pe, and this term will have the order of magnitude of alpha into tc by L into pe whole square. This term will have alpha into tc by L square, right? So now you see that uh, if we compare these two terms, okay, if we can compare all the terms. Okay, so but clearly this is the LHS and this is the RHS. So in RHS this term is having a Peclet number, right? This term is having a Peclet number. So for Peclet number greater than 1, for this condition we can surely can neglect this term. right? So that means our equation, governing equation, boils down to what? Our governing equation boils down to u, this is equal to alpha, okay, and from this we can define, okay, I have always told you that uh, we should define the non-dimensional variable such that, so this x bar is LPE, so this is of the order of 1, so this is beneficial, that to define the non-dimensional variable such that their order should be 1, okay. So what is the benefit? The benefit is that this non-dimensionalization will directly give you the essential physics. So here we can have y bar equal to y by L, and then we can have t bar equal to t by Tc, right? So here uh, you can remember that we took the same t bar, or let me write it as theta, okay. For the pipe case also we took the same theta, okay, and T in is what? T in is the inlet temperature of the fluid, okay. So this is the problem formulation. So then this equation becomes what? So then this equation becomes u, okay. So u delta theta delta x bar into, so T in minus Tw. I hope now you are comfortable enough with this, how to write these things. L into Pe, okay, equal to theta by y bar square T in minus Tw by L square, right? And what was Pe in case of the pipe flow? That was alpha, okay, Reynolds number based on L into Prandtl number, that will be u L, or actually it was W for the pipe, so W into not L 2R by nu and into nu by alpha, so that was 2R into W by alpha. So here this Prandtl number definition will be L into U by alpha, okay. So we can cancel out this thing and one L can be cancelled out. So what is remaining here? So del theta del x bar is equal to, there will be one Pe above, right, and alpha is already there, so I can write this as this, right. So if this is correct, then you see that this is the definition of the Peckley number. So this and this will be cancelled out, and the final governing equation, the non-dimensionalized governing equation, will be this, okay. So this is the non-dimensionalized governing equation, so let me name it as 1, okay. Now what will be the boundary conditions? So the boundary conditions, how can I find them? So first, in terms of the dimensional variables, at y equal to 0, I have my del t del y, my del t del y is equal to 0. So in terms of the non-dimensionalized variable, what it will be? At y bar equal to 0, my del theta by del y bar, that will be 0, correct. Okay, then what else I am having? At y equal to L, my del T del y. So, okay, so flux is not mentioned, the temperature is mentioned. This is equal to T wall. That means in terms of non-dimensionalized variable at y bar equal to 1, my theta is equal to 0, because theta is equal to T minus T wall by T in minus T wall, correct? Yes, right. This was the definition of the theta. Okay, and now you see in the equation we need two boundary conditions for y, because it is second order in y and first order in x. So one more boundary condition for x is needed, and that will be given by, I am writing it here. So at x equal to 0, my t equal to T in. If you go back to the definition of theta and x bar, it will boil down to at x equal to 0, theta will be 1. So let me name these equations also as 2, okay, then 3, then 4. So now I am having my 1, 2, 3, 4 defining my Graetz problem, okay, for the flat plate and with the specified boundary condition. So now let us solve it. You see the same type of equation we have arrived, okay, and how it is the same type of equation? You see this equation. So let us just compare. Can I just copy it for the purpose of comparison? Let me see this, so I can copy it. I am warning you that this Microsoft Office might misbehave, because now every time during this copying function it misbehaves. Okay, so paste. Okay, so now it is okay. uh, okay, so now you see this equation and this equation. I hope these two are visible. That is this equation here. What is happening? Okay, that is this equation here, this one. This was the governing equation for the Graetz problem for pipe, and here the equation 1 is the governing equation for the parallel plate channels. So the only difference is that here we were having 1 minus eta square, but here we don't have that, but otherwise this looks same. Here we have del theta del z star, here I am having del theta del x bar, and here also I was having the second derivative of the transverse coordinate. Here also I am having the second derivative of the transverse coordinate. And you see the boundary conditions at eta equal to 0, this is the symmetry condition. At eta equal to 0, my gradient is 0. Here also my at y equal to 0, y bar equal to 0, my gradient is 0. And then I am having at eta equal to 1, my variable is 0. So here also my at y bar equal to 1, my variable is 0. At z star equal to 0, my theta was 1, and here also at x bar equal to 0, my theta is 1. So exactly similar problem, just the form or the looks of the governing equation is a bit different. Okay, so now let me remove it, okay, because I don't need this. But now I will have a mathematically possible problem. I mean, the previous problem was also mathematically possible, but that was very cumbersome, and we we were to take help from the mathematical function tables. Okay, but now we can do this problem independently without taking help and anything. Okay, so now similarly we will solve this problem, and we will apply here the method of separation of variable. Okay, so here theta is a function of x bar and y bar. So let us write it as a of x bar into b of y bar. Okay, so I will give this equation a number 5. Okay, so from 5 and 1, so from 1 and 5, that is putting theta in the governing equation, that is 1. So what was the equation here? I am writing it fast, but you should always write it in by understanding. Don't copy from me directly, you should understand, okay, that what you are writing. So this will a into d2b dy bar 2. Okay, and then I can rearrange this equation as 1 by a dA dx bar is equal to 1 by b d2b dy bar 2. Now you see that this is a function of x bar only, this is a function of y bar only, and for this is valid for any x bar y bar pair, and that means this is only possible when each is equal to a constant, and we have shown physically, and the same argument also applies here. I will not tell the argument again, I have explained it in details for the pipe case, that this is, so this must be negative. So this we take as minus lambda square, where lambda is not equal to 0 obviously. Okay, we will see that if lambda is 0, then it will boil down to a trivial solution. So then first let us solve for this part, that is the a part. Okay, so what will this a part give? This will give dA by a equal to minus lambda square dx bar, right? Okay, so then a will be equal to some c e to the power minus lambda square x bar. Okay, c is the constant of integration, and let me number this as 6. Okay, so I think I have not done any mistake. Yes, I have not. So after that let us solve this equation for b. Okay, then this will be, now here is the main difference between the previous one, that is for the pipe one, and for this one. Okay, so here the equation is much simpler. Okay, and if you have done your course in differential equations, then you will come to know that this is having a solution of b is equal to some c1 sine of alpha y bar plus some c2 cos of lambda into y bar. So did I say alpha y bar for the sine case? In that case I apologize. Okay, and this can also be shown actually. I mean the general method I can show you for this equation. The auxiliary equation is d square plus lambda square equal to 0 for this. So d is equal to plus minus I into lambda. Okay, that means this b is c1 e to the power I lambda y bar plus c2 e to the power minus I lambda y bar. Okay, so then if we expand this e to the power I lambda y bar as cos of lambda y bar plus I sin lambda y bar, right, and then we can expand this also, then from those two we can write this b. Okay, so from this way I actually used to remember this solution. Okay, but now I have done this many times, so I don't need to do this thing, I can remember this. So this is B. So let me term it as 7, equation 7. Okay. So for B we have the boundary conditions. So B is dependent on Y. So the boundary conditions for Y bar only we will take. That is the equation 2 and 3. So equation 2 and 3 is saying that at y bar equal to 0, my dB dy bar that is equal to 0, and at y bar equal to 1, my b is equal to 0. Correct? We have to just uh, replace theta by b, nothing else. So this is equation 8 and 9. Okay. So to apply equation 8 on 7, we have to find the derivative. So from this equation dB dy bar, that will be what? So lambda will be common, then C1 cos of lambda y bar minus C2 sine of lambda y bar, right? And that at y equal to 0, so at y bar equal to 0, this will be 0, this sign, and this will be 1. So, and that is 0, we already know. This directly showing that C1 equal to 0, right? That means B is nothing but C2 cos of lambda y. Okay. Now let me term this equation as 10. So you combine 9 and 10. You combine 9 and 10, and that will give you that C2 cos of lambda is equal to 0. Now you have two options here, two options. One is C2 equal to 0. So if C2 equal to 0, then this option will lead to B equal to 0, and if B equal to 0, then this option will lead to theta equal to 0, because theta equal to A into B. So one obvious solution is theta equal to 0 everywhere, and this is the trivial solution. Okay. But we don't want this. So another solution is what? Another solution is cos of lambda is equal to 0. So this lambda is the odd multiple of pi by 2, right? Okay. So then this is the solution that will give us non-trivial one. Okay. So this will lead to the non-trivial solution. Okay. And this lambda is known as the eigenvalues. So these types of equations, okay, these are the, these types of equations, these. So these are the eigenvalue problem for differential equations. Okay. So these are the eigenvalue problem for differential equation. Okay. So and these problems, this class of problems have a particular name, and that is the Strum-Liouville problem. Okay, STRUM, and I don't remember the spelling of Liouville. Okay, so you can search by, and you can type the spelling by your guess, and Google will catch it. Okay, then you can see the formulation of the Strum-Liouville problem. Okay, so here we will have the eigenfunctions like the eigenvectors. So these are the eigenvalues. So this lambda is the eigenvalues. Why I am writing values, that is plural? Because I am having here n, right? And this n can have multiple values. This n is from 0 to 1 to 3. Now you can say that n can be negative also. So this okay, sorry for that. Now I will see that why we are not taking the negative values. So in the linear algebra we can find the eigen functions and given the eigenvalues and sorry the eigenvectors, and here I will find the eigenfunctions. So what will be the eigenfunctions? So here I am having the solution for lambda, that means from this I am having my b is equal to c2 into cos of lambda n, okay, into y bar, right? So these are my eigenfunctions. Okay, now I can write this c2 as some cn. Okay, for nth eigenfunction I will have a different constant cn. So this is my bn more specifically. So this is my nth eigenfunction. Okay, this is my nth eigenfunction. Okay, so now I do know this. And what are my lambda n? Lambda n is given by this. This is lambda subscript n. Okay, so now I can find my theta. So let me turn this equation as what was my last equation, that is 10. So this as 11, right? This as 11. So let me have a sip of water. I will continue after that. Okay, so now from equation 11 and from equation where we have find a 6, this one. So now we can write that our theta is equal to a into b, and that is there was c into e to the power minus lambda n square x bar into cn cos of lambda n, this one, right? And this is equal to theta n. Okay, so now you see that this equation, this governing equation is linear. So if theta 1 is a solution and theta 2 is also a solution, then theta 1 plus theta 2 is also a solution. This is a property of a linear differential equation. This equation I am talking about, this is a linear one. Okay, so if theta 1 is a solution, theta 2 is a solution, then theta 1 plus theta 2 must be a solution. So now here theta n is a solution for any value of n from 0 to infinity. And you now see that why I am not taking the negative values. So here cos lambda, if you put here instead of lambda minus lambda n, then it will be absorbed. Okay, so these are linearly dependent. So had it been not linearly dependent, then I have to consider them separately. Okay, that means let us say that if I am taking this here minus lambda, so then let us say that for minus lambda I am having this constant as minus cn, and let me write that as plus c dash n, and for plus lambda I will have cn. So then if I club those two terms as cos of minus lambda n y bar equal to cos of lambda n y bar, so then I can club those two terms and I will have this plus this into cos of lambda n y bar. So you see this is just giving a new constant, and which has the term as this. So I don't have to account for the minus 1. Okay, so now let me continue. So here the general solution will be theta is equal to summation of theta n for n equal to maybe 0 to infinity, and that I can write as equal to, okay, k of n into e to the power minus lambda n square into x bar into cos of lambda n, this one, okay, n equal to 0 to infinity, where this kn, this one, is equal to c into cn, okay. Now my problem is almost over, but I have to find this kn, right? How can I find this kn? Now you see there is something called orthogonality, okay. So orthogonality of eigenfunctions, okay. And what is that? So you take this equation, what, that is the governing equation for b, because b was the function which is the eigenfunction. So that was del 2b del y2 plus, right, what else, it was lambda square b is equal to 0, right? Yes. So now every b, that is bn, I should write here, every bn will satisfy this equation. So now what you can do is multiply this equation by b subscript m and integrate with respect to y bar. So this will be 0 to 1, okay. dy bar 0 to 1 equal to 0, okay. Now we apply integration by parts for this one. So this is having a higher order derivative, we want to reduce this, so we integrate this function. So I will have dbn bar, not bar, dy bar into bm, so this whole function from 0 to 1 minus dbn dy bar into dbm dy into dy 0 to 1 plus lambda square, this is equal to 0 to 1. Now you see here at 1, at y bar equal to 1, I am having bm equal to 0, right, and at so this is equal to 0 at y bar equal to 1, and at y bar equal to 0, this is equal to 0. So this whole thing, this must be 0, okay. So now that means I am having only this part, that is integration of 0 to 1, okay, lambda square bn, this one dbm, okay, dy bar is equal to 0, right, okay. So now you see that if I swap here m and n, so next step will be swap m and n, okay. So this will be, why I can swap m and n and this and still this equation should remain same, because you see that here this n was not having any specific identity, this n can any number, similarly this m can also be any number. So had I started with m, then also the total mathematics will be remain same, okay. So that is why I can do this swapping, otherwise not. So there it will be this minus dbn dy dbn this thing, right? So am I doing the right thing? I think so. um, Let me see, this is equal to 0, right? Okay. Okay, so one thing we have done it very, sorry for that. Okay, my water bottle just fell down. So one thing we just have missed, that is this is lambda subscript n. Okay, because along with the nth eigen function we cannot consider any eigen value, right? So this is lambda n everywhere, but after swapping m and n, this becomes lambda m, right? Now it is okay. So you name these equations as, so how many equations were there? So 11 was there. So let me term this as 12 and this as 13, this is 14. So you do one thing, that is 13 minus 14, and that will be what? That will be lambda n square minus lambda m square into bm into bn dy bar. Okay, that is equal to 0. Okay, so my battery is dying, so I have to stop here, but let me just complete it. Okay, so this is equal to 0, right? Okay, so lambda is not a function of y, so then I can write it as this. Okay, integration is equal to 0. Okay, so then you see that this can have two options again, right? One option is lambda n is equal to lambda m. Okay, then this is 0, then I can say that I can have this one. Okay, then this is not equal to 0. Another option is lambda n is not equal to lambda m, then this must be equal to 0. Okay, so that means this means n equal to m, and this means m not equal to n, right? Because lambda n is equal to lambda m, that means n equal to m. Okay, because all the eigen values are distinct, and lambda n is not equal to lambda n, that means m not equal to n. Okay, so this is my orthogonality condition, that is, I mean this thing, nothing more. Okay, this is my orthogonality condition, and if my m equal to n, that means this boils down to uh, bn square dy, this is not equal to 0. Okay, so that means this integral, okay, this is not equal to 0 if m is equal to n, and this is equal to 0 if m is not equal to n. So this is the orthogonal property of the eigenfunctions. Now in various cases we can have some another function multiplied here given by w. That means I can have something like w into bm bn dy bar. This is equal to 0 if m not equals to n, and this is not equal to 0 if m equal to n. I can have a function w like here. So here this w is called the weighting function. Okay, okay, and you see that this product, I mean this integral is called the inner product between bm and bn. Okay, in terms of the uh, function space. Okay, I will not go into that. So this was the orthogonal property. So we can apply this one to find this constant kn. How? So let me now apply this. Okay, now let me write this theta n. So theta is equal to theta n, that is equal to, so kn, right, kn e to the power minus lambda n square x bar into what else, into cos of lambda n y bar, correct? Okay, n equal to 0 to infinity. And we also know at x bar equal to 0, theta is equal to 1. That means my 1 is equal to this n equal to 0 infinity kn cos of lambda n y bar, because this term will go to 1. Okay. So now you just play with this equation, that is multiply by cos of lambda my dy and integrate in both sides. Okay. Just do it, multiply. Okay. Then you see uh, this term I can modify as, so I can take this integral inside the summation, because summation is not over y bar. Okay. So summation I can take it out. Okay. Then I can write it as kn cos of lambda n y bar into cos of lambda m y bar dy 0 to 1. Okay. Now this integral, you see kn I can take it out. So this integral, if I finally write it like this, bn bm dy, right, because bn is cos lambda and y, n equal to 0 is this. So this is having a non-zero value only if I write this, that is m equal to n. Okay, m equal to n, otherwise this will be 0. So I can write m equal to n, and this is also equal to km 0 to 1 bm square dy, and that is equal to kn or m, anything, cos of lambda n y bar whole square dy, right? And we are having the formula for the cos square n, and I think this is pi by 2. Okay, or maybe this is half, 0 to 1, so maybe this is half. Okay, into half. Okay, so if this is half, you just do this integral and this will come out to be half. So now we can find that, and this equation we can have the value, that is what, so cos, the integral of cos is sine lambda n, so this is sine lambda m into y. Okay, that is fine, and this is equal to km into half, right? So then we can find this km as 2 into sine of lambda m. So we have now the form of the km. So here in this equation, I think I have written, yes, in this equation I have this as 2 into sine of, okay, sine of, I think that was lambda m, yes, lambda m. So if you are considering n here, then you have to consider n here, so this will be 2n plus 1 into pi by 2. Okay, because this was the value of lambda. So this completes our solution for the temperature profile theta. Okay, so now I don't have enough charge in my iPad. Okay, so I will continue in the next discussion with finding the Nusselt number and the wall. I mean the Nusselt number, obviously the Nusselt number and the wall heat flux. But up till that, your homework is to formulate the problem for psi that I did for the uniform wall heat flux problem. So there was the governing equation of psi, and you have to solve that equation. At least you have to formulate up to the separation of variable. Okay, that part. Okay, that means you have to write the governing equation in terms of this, because I have already shown you two problems. Okay, so you have to do it, and you have to convince yourself that if for z tends to infinity, psi is going to 0 or not. If this is not happening, then our total solution is wrong. Okay, so you have to convince them by solving for psi by the method of separation of variable. Okay, so that is your homework. So and up till that, goodbye, take care, and thank you.